Okay, next question. HCN with H2PO4 sodium hydrogen phosphate. Okay, so for sure the sodium hydrogen phosphate first splits up again into hydrogen phosphate and the sodium, and so that becomes easy. That's just H2PO4 minus, which is right there. What happens then? The H2PO4 minus will react with the HCl. But what is HCl in solution? You all know that that is a strong acid. And when we say it's a strong acid, we simply say that we look at it in the form of H3O plus as a reactant, and Cl minus is again a spectator ion in solution. Now, what is the reaction that can possibly take place? Actually, the reaction that can take place is, well, you know that the H2PO4 can be both an acid or a base, but since it's reacting with the very strong H3O plus, it's definitely going to act as a base. And that's going to this is going to be your base, so it's going to pick up a proton from H3O plus, and it's going to become H3PO4 and water. What is the Kr, guys? What's the Kr? Well, I'm going to do it the long way now. The Kr will be the Ka of, sorry, the short way. Kr will be the Ka of the acid on the reactant side divided by Ka of the acid on the product side. Who's the acid on the reactant side? It's the H3O plus. Who's the Ka on the product side? It's the H3PO4. So that's the Ka of H3PO4. We always put it in the form of a couple, but you can just say Ka of H3PO4. What's the Ka of H3O plus water solution? Or H3O plus, what's its Ka? Yes, the Ka is 0 because the pKa is, the Ka is 1 because the pKa is 0. And you all know that H3O plus with water, the pKa of it is 0. It's the lowest on a pKa scale for us in general chemistry. So that's a 1 divided by the Ka of H3PO4. I could have said that, could I not? Look at this equation. Isn't just this the opposite of, the reverse of the equation of the Ka of H3PO4? Remember, H3PO4 plus water becomes H2PO4 minus and H3O plus. That is Ka1 on the opposite side. So this is 1 divided by Ka1. Okay, which happens to be 10 to the 2.2, which is much greater than 1. It's almost 100. All right, so what is this reaction? It is very much advanced in the forward direction. And that's just another way of putting my Kr, pKa of products minus pKa of the reactants, 10 to the power of that, which is 10 to the power 2.2 minus 0, which is simply the same answer. Now, I just want to put this, and this is in green. In other words, pay attention to whatever I have in green here. Yes, the Ka is not complete, okay? This number is not 10 to the 4 and above. It's not quantitative, it's not complete. However, there's a rule that we are going to take in organic chemistry. In general chemistry. And that is, anytime you see a strong acid or a strong base as a reactant, okay, we usually consider that the reaction goes in the forward direction, and we usually assume that the reaction is stoichiometric and treated as complete. Okay? The reason is, there's no such thing as H3O plus in real. Guys, if I want in solution, I can't sit there and buy a solution of H3O plus. I have to buy a solution of HCl, HBr, HI, H2SO4, perchloric acid, or nitric acid. So there's no such thing as H3O plus. What do I mean by that? I mean that the pKa here is never really 0. It's always lower than that because it's really the pKa of HCl, which is lower than 0, okay? And that means that my Kr, this is not really this number. It's always going to be higher than that, Okay, so just take it as a rule that anytime I have H3O plus reacting with something else, we usually go to completion. Okay, the reaction goes to complete. At least you will see this when we get to titrations and or buffers. Sometimes we add H3O plus to a buffer. You're going to see that always that reaction goes to completion. Question number 13. We have a mono acid HA with a pKa of 5 is mixed with a mono base with a pKb of also 5. So the pKa and the pKb are very close to each other. They're exact here. So I have acid and a base mixture. They're asking you, MCQ, the proton transfer reaction HA plus A plus B is complete. Is it? Well, we have to see. If I am asked to be, is the reaction complete or not? What do I have to do? I have to find the K reaction, okay? So part B, the reaction HA plus B shifts strongly towards the product. Well, if I know also the Kr, I will know if the reaction goes product or it doesn't. The equilibrium reaction constant is 10 to the minus 10. In other words, go ahead, find the Kr. The equilibrium reaction constant is 10 to the 4. Well, we have to do the calculation. The equilibrium reaction constant cannot be calculated without additional information. Wrong, of course, I can calculate it as long as I have the pKa of both. I can calculate it. Well, this is a base, but I can still get, if I have pKb, I can get its pKa, of course. What is the reaction that's going to take place? Well, I don't have a choice. HA is surely my acid because the B has no protons. So the reaction will be HA plus B becomes A minus and BH plus because the P picks up a proton and it's neutral, so it becomes BH plus. So here's my reaction. How can I calculate the Kr? Well, Kr is 10 to the pKa of the product acid minus pKa of the reactant acid. Do I have the pKa values? Of course I do. I have the pKa of HA, that's 5. What about the pKa of the BH plus? Well, I have the pKb of the base, so I can get the pKa of the BH plus. 14 minus the pKb will be 9, so that is my pKa value of the BH plus. Okay. If you want to put them on a pKa scale, though really if you have two reactants, you don't have to put them on a pKa scale. The reaction is a bit obvious. And simply get the Kr, gonna be 10 to the 9 minus 5. So 9 minus 5, that's my change in pKa value. That's my 9, that's my 5 products minus reactants. 10 to the power of 4 is my Kr. Automatically, do I need to show you that this actually goes in the gamma direction? No, I don't have to show you this to tell you that the reaction proceeds because the Kr is greater than 1, okay? If the Kr is greater than 1, the reaction is gamma and it proceeds in the forward direction. Of course, if my products have initial concentration of 0, we will see this later on that sometimes we have to calculate Q, but keep that for later. The reaction between HA plus B shifts strongly towards the product. Of course, it shifts strongly because look at the Kr, it's 10 to the 4. Is it complete? Well, we will see. What's the equilibrium reaction constant? It's 10 to the 4. Part A, they asked you, is it complete? Well, I'm going to tell you that to be the idea of complete, it means that the Kr has to be greater than 10 to the 6. We did this at the beginning, at the first part of the beginning of this course, in the introduction, where we talked about many things that we're going to use later on. This is one of them. We actually did a calculation. We showed you that alpha, when alpha is 0.999, the Kr of the reaction has to be 10 to the 6 and above. And we said that if the Kr is, the alpha is 0.99, so 99% complete, we get a Kr of 10 to the 4. We called this quantitative, but then we said, and I said clearly, that if I have a reaction which is K reaction greater than 10 to the 4, in reactions, the reaction, when I'm doing a calculation, I treat it as complete. But the theory, in theory, this is called quantitative, and Kr greater than 10 to the 6 is called complete. In other words, is the reaction complete? Well, no, it's not, but it's treated as complete if I have to do calculations. So the only answer is B and D. Number 14, consider the following: a mixture of methanoic acid, HCO2H, and its conjugate, nitrous acid and its conjugate, is suspended according to the following equation. So they gave us an equation already. So as written, they have already given you an equation. Now, if it goes forward, backwards, we will see. But they gave you an equation, okay? And they gave us also the pKa values. They called the pKa for this acid, the methanoic acid, they called it pKa1, and they called the pKa of the nitrous acid, they called it pKa2. And they gave us the Kw. They asked in part 1, this is a 6-part question, so in part 1, what is the equilibrium constant K? When I have a reaction, it means the K reaction. What is the K reaction, guys? I'm not, I'm going to show you how to do it, but right away, you should say the K reaction is Ka of the acid on the reactant side divided by Ka of the acid on the product side. So if I look here, what is the only expression? Is it Ka1 divided by Ka2? Well, that's how we said it in the course, but I have to watch out. They switched them here. Look what they called this guy Ka2 and this Ka1. So the reactant acid is my Ka2 and the product acid is Ka1. And watch out for this. So that we really, بالconcours especially, we like to confuse people by such things. This is indeed the stronger acid, and yet they called it pKa2. All right, so regardless, watch out. Still, just in case you forgot how we got that, we're gonna still put it for you. So here is, I put the equation, I make a statement, pKa2 right away. I like to put the pKa's underneath each of the acids on the reactant side and on the product side. Place the two acids on a pKa scale. And let's see, does it proceed according to gamma rule? Let's just take a look. Indeed, the H nitrous acid is nitrous acid is the stronger acid. And if this is the stronger acid, that means that the other acid is the weaker acid. It has a higher pKa. This has a lower pKa. And therefore, its conjugate, methanoate, is the strongest base. So that's the stronger base reacting with the stronger acid. Voila, gamma. And so does the reaction proceed? Yes, it does. It proceeds according to gamma, and the reaction is thus considered spontaneous as written. Now let's again go to deriving the K reaction. I don't really think that you have to go that far, but still, again, this is course-wise, reminding you of the course, how we derive the K reaction. Again, the Kr of the reaction is products divided by reactants. You just do that. And what do I have here? Products, I will split the two couples. nitrous acid with its conjugate and acetic acid with its conjugate. You will notice that here, if I multiply by H3O plus on both sides, what is this expression? Yes, indeed, that is just the Ka of the nitrous acid. What about this one? That's 1 over the Ka of the methanoic acid, and that means this happens to be Ka2, that's for the nitrous acid, divided by Ka1. All right, do the calculation, and you get that the K reaction is, as a number, 10 to the 0.6, because this is 10 to the minus 3.2 divided by 10 to the minus 3.8. What is this number? This is almost 4. It's 3.981. So what is the K here? It's the K reaction is Ka2 divided by Ka1. So my answer is C, which I could have gotten centuries ago. Just if you had remembered that always the K reaction is the acid Ka on the reactant side divided by the acid Ka on the product side. Okay. Calculate the numerical value of K. Calculate the numerical value of K. Of course, we just did that, so I'm not going to do it again. That's the numerical value. So do the reaction. What is the number for the numerical value? There it is. And so the answer here is, of course, 4. We could have done K reaction differently. K reaction is 10 to the change in pKa value, which is 10 to the pKa of the products minus pKa of the reactants, which is 10 to the 3.8 minus 3.2. Watch out, guys. Here, it's a pKa of products minus reactants. Okay? A little bit different, so don't get confused by the two expressions. Okay? Number 3, very, very, very nice. I love this question because it really hits close to home that we don't always say that if K is greater than 1 and therefore the reaction proceeds spontaneously. Again, if I have a reaction and I have reactants and products, I have to relate K to Q in order to say if the reaction proceeds or does not proceed. Let's forward or spontaneous in that direction. Okay, so let's look at what is this question 14.3. The initial concentration of the mixtures, so that's, we're talking about the same reaction. They gave me the initial concentration of the reactants and the products. And they asked, what is the value of Q, which is the reaction quotient? Now, of course, most of you even forgot what Q was. Indeed, that was during the introduction chapter, but just as a reminder, Q is the same expression as the K, except I use the concentrations at any particular time, not necessarily at equilibrium. In this case, they're asking for the initial reaction quotient. So I'm going to look at the expression with the initial concentrations. So if I have this is my reaction, which they gave to you, and they asked for Q, so you say products concentration divided by reactants concentration initial, because this is the Q initial. Okay, let's do that. Do I have every single species here? Yes, I do. Let's do the calculation. What's the concentration of HNO2? Well, you have to watch out for how this is given. This is going to be equal to this number because there's nothing in front of the nitrous acid. So I don't have to multiply or divide by anything. What's the concentration of HCO2 minus? That's also equal to 3 times 10 to the minus 2 because there's nothing in front of here. What's the concentration of NO2 minus? Well, there's a number in front of it. So what I have to do, if I want this NO2 minus, I have to divide by 2 here, and so I have to divide this number by 2, which becomes 1.5 times 10 to the minus 2. Likewise, the product is also here, HCO2H is also, I have to divide it by 2 because there's a number in front of it, so I divide this number by 2. Great. My Q will be the products, which happens to be both 1.5 times 10 to the minus 2, divided by the reactants, which both happen to be 3 times 10 to the minus 2. Do the calculation, you get that Q is 0.25. Now, what's the answer? Q is 0.25. Great, I'm done. But let's look at part 4. They're asking you, in which direction will the reaction take place? And which reaction? I'm talking about the one right up previous to it with the calculation of Q. So to know the direction, we have to relate Q to K. What is Q? Q is 0.25. We just did that calculation. We notice 0.25 is less than K, right? Okay, so if Q is less than K, what does that mean? It means, just going back for a moment, means that I don't have enough products because this Q number is less than what my K at equilibrium is. It means that I need to go more in the forward direction to get me more products so that Q can be close to K. So if I need more products, that means the reaction goes forward. And indeed, anytime your Q is less than K, the reaction system will proceed in the forward direction. What's the forward direction? That's direction 1 in the reaction we just spoke about. And so my answer is A. Is the reaction complete? No, it's not, guys. It's not complete because anyways, K is just 4 and the reaction will not go to completion. You don't have to take all the reactants to get. The reaction is non-existent? No, because the K value, again, is greater than 1, so the reaction exists and it can proceed, and it proceeds in direction 1. Action there. That should have came a little bit earlier, but okay. So it proceeds in direction 1. Calculate the pH at equilibrium. Okay, so here I'm just going to do something very fast, and then later on I will do a more decent calculation. pH, well, okay. I have some initial concentration. We said that that concentration was 3 times 10 to the minus 2. I'm just going to put C0 for simplicity, but we do have a number for that. And we had initial also concentrations, which were half the amount of this, but we're just going to say B0, okay? The reaction, of course, proceeds in the forward direction, but there's a rule that says, if my concentration, okay, of reactants are the same for an acid-base couple, and if my concentration of products are the same for an acid-base couple, in other words, if HA equals to B minus, in this case, and A minus is equal to HB, then we can say that the pH of this type of solution, which is an acid-base mixture, this is not a salt, this is an acid plus a base, but that can be treated as if it's an amphoteric salt. And the pH is actually independent of whatever the concentrations. Even if no matter what these concentrations were, I don't really care. I just care that this concentration is the same as that and that the product concentration are the same. If that's the case, I could simply use that the pH equals half pKa 1 plus pKa 2, and you have pKa of the first acid and the second acid. It doesn't matter which one you put first. Okay, So actually here the pKa2 is the 3.2, pKa1 is the 3.8, okay? But who comes first, it doesn't really matter. It's the pKa's of the acids equals to 3.5. Again, a more detailed derivation will be given to you, okay, in question number 32, okay, not here. Here, I really want you to concentrate just on if these two are equal, then you use this equation. Answer is simply D. Even if this reaction, like I said, if it proceeds forward or backwards, I'm still going to have minus x, x, but still this number is also equal to that number. Okay. Now, as a briefing here. So I have initial concentrations, minus x plus x, once the reaction proceeds, and I have a Kr value, and my Kr is, in this case, products divided by reactants. Let's look at this in detail. Products will be, again, I'm proving to you that all I have to do is use pH equals half pKa1 plus pKa2. But I'm going to do it the long way now, okay? Long way, it tells you that, okay, let's do the reaction. Let it proceed in the forward direction, minus x plus x at equilibrium. And these are my equilibrium concentrations of all the couples, or the reactive couple. So this is B initial plus x squared, because this is equal to that. And this is C minus x squared, because these two are equal to each other. And it happens that my Kr is equal to 4. Great. Now I want to solve for x and get an actual number for x. Let's do that. Find what x is. The reaction actually, when these guys are the same, the reaction becomes easy because I can take the square root of both sides. Take the square root of both sides first. So you get here 2. This becomes B initial plus x divided by C minus x equals to 2. And then multiply the C minus x by the 2. And then solve for x. Get all the x values on one side and all the numbers on the other side. So this becomes 2c, take the b to the other side, minus b, take this x to the other side, this becomes x plus 2x, so which is 3x. Solve for x. We know that C initial was 3 times 10 to the minus 2 from the previous question. And we know that the B initial is 1.5 times 10 to the minus 2. Now I made this little star to be the time so I don't confuse it with the x, okay? Solve for that, what do you get? Well, solve for x, you get that x is 0.15. Now once you have the x, what does that mean? That means I have the concentration of every single species in my solution. Look at it. So I have C0 minus x, I can simply solve. C0 I have, I subtract the x, I get a number. Okay, so I get the numbers. What numbers do I still see? I still see equal amounts products and equal amounts of reactants. Of course, I will always get that. And the rule says that once I have two couples in solution, my pH can come from either couple then reacting with water. Okay, I can take either couple and react it with water. So it means that my HNO2 plus water becomes NO2 minus plus H3O plus. Therefore, I have H3O plus in my solution. Okay. Also my base, because look, but now we have higher concentrations of the acids, right? In this case, I have more acid. In this case, I have less acid. It doesn't really matter who you start off with here. And there's a rule that you can say that if I have two couples, nitric acid and the nitrite, the pH, when I have the two couples and I have their concentrations in solution, we simply use what is called the Henderson-Hasselbalch equation. And I derived for you in at the end of last course recording the Henderson-Hasselbalch, and I said that the Henderson-Hasselbalch is very useful when I have the anion and the acid present in my solution. And it's simply pH equals pKa of that plus log of the base divided by the concentration of the acid. Well, and this is also for the other couple, pH will be pKa of the formic acid plus, or methanoic acid, plus the log of the base divided by the acid concentration. Well, for that, okay, let's look at this. pKa of the nitrous acid was 3.2 plus log of the concentration of NO2. Oh, where is that? Where is that? NO2, there you are, 0.03 divided by the concentration of nitrous acid. Where are you? Oh, that's 0.015. What's the answer? pH is 3.5. What about the other methanoic acid? Well, the pKa is 3.8 plus log of the base of methanoic acid. Where are you? Oh, there you are, 0.15, divided by the acid of methanoic acid, which is 0.03. Oh, the same answer. Did I have to do the calculation for both? No. What did I get as an answer, guys? That the pH is 3.5. pH is 3.5. Let me just look backwards. Tick, 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 back, without doing all this long way. Look at this, pH of 3.5. Oh my God, all I had to do is pH equals half pKa1 plus pKa2, and I have my answer, okay? You don't have to do it the other way. I don't have to calculate X. I don't have to get this concentration of every species in solution. I don't have to do that. Okay? I simply, if my concentration of acid on the reactant side is equal to the base on the reactant side, and if the concentration of the product, even if it's 0, 0, it means that their concentration at equilibrium will be X and X. That will be equal to each other. And if I have some in solution and they're equal to each other, well, at equilibrium, they're also equal to each other. When that is the case, you simply use pH equals half pKa1 plus pKa2. Save yourself a lot of time. Okay? And look what I had to do in order to convince you that I don't have to use this all. I simply use half pH equals half pKa of one of the acids and plus the other acid pKa. And the last question of number 14 is the following. In a new mixture, they changed my initial concentrations, okay? They didn't change the reactant concentration. That's still 3 times 10 to the minus 2, but they changed my product concentration. Wow, great. They left them the same though, but now I didn't multiply by 2. This is 0.1, so I have to divide this by 0.1. And they still ask the same question. Does the reaction go forward and in direction 1 or direction 2? Is the reaction complete and or non-existent? So if I need to know if the reaction goes forward or backwards, does the K help me? No, the K on its own. Remember, the K doesn't change for the reaction. K is still equal to approximately 4 here. We did that, we calculated that. But if I have products and reactants both in my solution, just looking at K, I cannot say if the reaction goes forward or backward. I can't talk about gamma at all, okay? It doesn't, if I have 0 reactants, that gamma doesn't apply, okay? What applies is Q related to K. Great, so let's calculate Q now. Q initial, according to these new initial concentrations. Here's my product's concentration. Again, if I divide this number by 0.1, we get 3 times 10 to the minus 1. That's the product. Now that my product concentration has changed, but they're still both the same, and my reactant concentration are still the same. What do I get? I get Q of the reaction is now equal to 100. If now I compare Q to K, remember K was 4, 100 is greater than 4. So Q is greater than K. If my Q initial I have greater than K, what does that mean? It means I have to go backwards. I have to decrease the products. The reaction now will go in direction 2. Okay, it will go in direction 2. The reaction will proceed backwards. It won't proceed forward, it will go backwards in direction 2. Okay, towards the reactants, not towards the product. Very nice question, very effective. Now, just out of curiosity, if I asked you to do the pH now for these, for this, when I have these concentrations, what will the pH be? Well, try it at home. I'm going to tell you that the pH will not change. The pH is still independent of the concentration. And even if I'm going in the opposite direction, remember the pH equals half pKa plus the other pKa. So it doesn't really matter which direction my acids is. Okay, so the pH will still be 3.5 even if I have less or more reactants or less or more products, because they're the same amount. Both of these are the same. All right. Well, stay tuned for the hardest question, which is number 32. And before I do number 32, I'm going to do some theory. Okay. Sure you try it on your own, and I'm hoping you are trying them on your own, okay? And the meeting.